In this activity, we're going to get some practice using the doubling hypothesis. So as you recall, doubling hypothesis is a way we investigate empirically the performance of our algorithms. And the idea is pretty simple. Basically, we run our algorithm at a certain input size, we'll call it n, and then we measure how long it takes. And then we double it, and then we measure how long that takes. And we keep doubling it, and what we do is we come up with a table like this, and we can compute the ratio. So as we double the input size, what happens to the time it takes to run the algorithm? And from that we get a ratio, and that ratio helps us come up with a hypothesis about what the order of growth of the algorithm is, at least ballpark, and we can detect differences between a linear and quadratic or a cubic algorithm. And in this activity, what you're going to do is get the zip file from the website, and what I've given you is a class where I haven't given you the source code. So the mystery class, you don't have the source code. It just has 4 static methods in there, and the methods all take some arrays and do some calculations, and I think return an array. And your job, without seeing the source code, is to try and determine what the order of growth is. So say these different methods, maybe they do all the same thing, and you just want to determine which one's the best one to use for a particular problem. Alright, you should be careful, avoid timing input and output, so don't time how long it takes to set up the arrays as input or how long it takes to output them. So you might want to even comment out the output when you run your experiments. And fill out a table and change your n to try and get a nice table. And usually you want to measure, so you're getting, you don't want to wait forever for your experiments to run, but you don't want to measure things that are really short, like hundredths of a second. So you want to get nice results or in this the whole seconds sort of resolution. And start small, work bigger. Some of these algorithms are quite slow, so if you start at 1,000,000, your computer may never finish. So start small and work your way up to try and figure out what a good range is for a particular mystery one. And once you've got that, come up with your hypothesis about the order of growth. And once you have your equation, t equals a to the n to some exponent, then solve for the constant a by using one of your sample points. All right. And let me show you, here's the program that uses the mystery class. And so what it does is it takes a single command line argument, and that's the size of the 2 arrays. It sets these 2 arrays up and then fills them with random data. Okay, so this could take a little while depending on how long it is, but we're not really interested. All 4 algorithms have to do the same setup essentially, so it's constant between them. Alright, then we run our calculation, pass the 2 arrays in, get a result array, and then print them out. And so you probably don't even, you probably should just comment this printout code out when you're, because this can actually, printing stuff out to the console can take quite a long time, and so you might not want to sit there and wait for that to happen. Alright, and you want to time just this inner part, the computation, and to do that I've given you a stats class, and it works pretty simply. If you just create this object stats, it starts a system timer, it makes note of the time, and then at some future point you can get the number of elapsed milliseconds and then compute the, this method computes the elapsed time in seconds. And then you can print that out and make yourself a little table and then see if you can figure out the performance. So go ahead and do that, and then when you come back I'll do the same experiment and you can see if you get the same answers. Alright, so first thing I'm going to do is let's do the timing calculation, and I'm just going to put a printout at the top of this, something that's done loading data. Okay, just so we know, and then that's done. Then I'm going to create my stats object, stats equals new stats. That will start my timer off, and then once I'm done with my calculation, then I'll go ahead and print out the elapsed time in seconds from that object. Okay, and like I said, we don't really care about this output, and it can take a long time to output, if we're doing millions of things. So we don't want to watch a million things scroll by, so we'll just comment that out. Okay, now let's see We can run the Java performance class, and we can run with something like 100. Okay, that took, you know, 1,000th of a second, so maybe we would crank up. Okay, and you can see this one we're cranking up on order, going up by orders of magnitude. So I'm just searching for sort of a number that gives me, you know, sort of a measurable time. And so that's pretty good. What is that? That's something like 10 million. All right, we'll call that our first data point for mystery A. So 10, 1, 2, 3, 1, 2, 3. Okay, and that took 0.62 seconds. All right, and I assume let's make sure I've done that right, so I can paste that number into my window here. Make sure we get the same number. Yeah. Okay. Yeah, and you can see there's a little bit of variability, but it's fairly consistent. Every time I run it, I get you know a somewhat similar thing. So doubling hypothesis, what we're going to do is double it. So change the 1 to a 2. Now we'll run it again. Alright, and I'm going to cheat here and just make a formula so I don't have to keep entering lots of zeros. And there's my time for the second run. I can now crank it up again. Okay, 0.257. Double it again to 80 million. .5 seconds. Alright, and maybe we'll do one more maybe. You can see now actually it's taking quite a lot. That loading of the array is actually taking quite a lot of time. The algorithm, you know, is going quite quickly, all right, in less than a second, but it's actually spending quite a long time just loading that data. Okay, well we could probably call that good, and let's see what our ratios are. So what we're interested in the ratio between, say, B7 here and B6, you know, and so I can write a little formula in Excel if I want. Okay, and calculate the ratio, and then if I copy this up, all right, and we can see, well, what do we conjecture about mystery A? Well, we believe mystery A is probably t equals, you know, a to the n to the power of, power of 1, right? So doubling hypothesis, right? If we're seeing if we're doubling and it's doubling, that means we've got a linear, okay, t to the an kind of equation. So that's a very good order of growth. That's our conjecture for that one. Okay, and if we wanted to calculate the constant for this, what we can do is we can plug in the time from our last sample. All right, so essentially what we have is equation 0 equals 0.994 equals a to the end of the first. And what was our n? Well, our n was this, you know, 16, you know, well, 16e to the, okay, that's basically the equation, right? And what I'm going to do is solve for a. And so to solve for a, all I need to do is take this number and divide it by that number. So I can do that in formulas in Excel. Okay, and solve for my constant a. Let's do mystery B. Alright, so first we need to come in here and change the code. Okay. And we'll start back down. Okay, 100, 1,000. Oh, 1,000's already taken 1 second. So maybe we should go back down to something smaller. Maybe start at 500. Yeah, let's start at 500. Okay, the exact specifics not. So all I'm doing is searching for something that's, you know, like a fractional part of a second, but long enough that it's, you know, accurate to measure. So notice we're starting this one at 500 while we started this one at, you know, 10 million. So obviously this algorithm's got a order of growth that's not quite so good. Okay, I can start at 500. There's no reason I have to start at any particular number, but now I need to double that number. So now I go to 1,000. Okay, I'm already up to a second. Go to 2,000. Okay, and probably time to sip some coffee here. 8 seconds. Whew. Dare we double it again? I don't know if I got enough coffee for this operation. So you can see, I mean, you can see just looking at this data, right? What do we think the ratio is? Well, you know, without even putting in a formula, it looks about, you know, we've gone out by about a factor of 8 times. So I can copy the formulas here, and you see the first ratio was 7. and this ratio was about 7.8. Okay, and you know, one nice thing about this is, if you know this is going up every time this goes up by about a factor of 8, what do we expect this to be? Well, about a factor of 8. So how long am I going to be waiting? I'm going to be waiting, about a minute before this thing finishes. All right, because we expect it to be about 8 times 9 seconds. All right, and even without waiting for that data point, we're going up by a factor of 8. So I'm suspecting this is a equation that's of the form the time goes as n cubed. All right, and that's because the ratio is 8, and 2 to the 3 equals 8. All right, in this case it's a 1 because 2 to the 0 is or 2 to the 1 is the sorry, 2 to the 1 is the 2. All right, anyway, okay, so we've got our final time in there. So it's pretty much as predicted, and you can see the ratio has gone to 8. And we could do a similar calculation here. We could take that last time that was in E6, all right, and divide it by now we've got to divide it by the problem size cubed. All right, so we've got, this is n cubed instead of just n over here. So here we're able to just divide it by n because the equation was n to the power 1. But now we need to divide this guy by this guy, cubed. And I don't remember what I guess there's probably just the caret operator, but all right, and we can get a constant value for that guy. So it looks like mystery B is probably n cubed. Let's put in mystery C, and we'll start him down low again, and I'll just search for a bit. Okay, so go up a little bit more, maybe 10,000 is probably good. So 10,000 giving us a decent starting point. We'll start mystery 3C at 3,000, or 10,000 rather. And we're getting 0.078. Let's double it. Okay. And we're getting 0.305. Double it again. Alright. 1 second. And what's it already looking like? Well, it's already looking like about a factor of 4, looks like. Alright, maybe we'll do one more. So the prediction here, it's probably going to take about 20 seconds. Alright, so 5 seconds times 4, it's going to be about 20, because it looks like the ratio is going about up 4 times. Yep, so 21,446, and I can copy my little formulas over here. Okay, and you can see, in fact, yeah, and it's not perfect, right? This one's a little bit off, but closest power 2 is 4, so we conjecture this guy is t equals a to the n to the power of 2, and again, you could compute that constant by taking the biggest time, and then we'll divide it by the 160,000 to the power of 2. Okay, that leaves us just with mystery D. We'll put mystery D into the fray. And we'll start him off low. Oh, okay, we probably don't want to go, we don't even start off. We start off even smaller. Let's start at 50 this time. This guy's not looking so good, is he? Alright, at 50, it's taken 0.05 seconds. Double it to 100. Okay, 389, double it to 200. And 6.455, double it to 400. And we can put in our ratios here. Okay, and you can see this ratio is not, it's not very consistent right now, right? We've got an 8 and we got a 16. So is it, n cubed, or is it n to the 4th? Well, usually you're going to see, if you're going to see sort of measurement errors, they're going to sort of occur down here at at the low end. And so I suspect this is a more accurate measurement. And if we're going by a factor of 16, then what's our prediction? We got a couple minutes to wait before this guy finishes off. And so I'm not sure I'm going to necessarily hang out for that. And I would guess this is end of the fourth, just looking at this first data point. So I could adjust, and do maybe a different value of n to try and get something. 400 is going to take some time. And again, you could do the same calculation to come up with the constant value for this. You could do k5 divided by j4 to the power of 4. So divided by n to the 4 and get your constant value. That's the basic process for doing empirical performance analysis. And I actually have the source code for Mystery, and if you want to see what they're actually doing, so none of these algorithms do anything particularly useful. It's just they just loop over some data and calculate some things. And we can see that Mystery A, it has what you probably would expect to see for a linear algorithm. You've got a loop that goes up from 0 up to the length of that array, and it multiplies the two. It's taking like a dot product of a vector or some such. Okay, and that was the one we came up with. Remember, we came up with Mystery A was linear. All right, that's typical form of a linear algorithm. Mystery B, where did Mystery B go? It's in a different order for some reason. All right, Mystery B has 3 for loops, okay, nested for loops, and they're each going from 0 up to n. And that one should look, it looks very much like n cubed, and in fact, empirically, that's what we found. All right, Mystery C, which is up here. We've got 2 loops, both going up from 0 up to n, and we found that guy was n squared. And finally, the slow as molasses machine D. Oh dear. Okay, 4 nested loops, and it's doing some, I don't know what it's checking mod and doing something, but it doesn't really matter. We've got 4 nested loops all going from 0 to n, and that's why this guy is so slow. And we got 102, and we could, if we wanted to plug that in, we can see if we can kind of confirm. Probably a little suspect taking this on faith. Probably good to get another data point, and in fact I was correct. It's looking very much like a ratio of 16. So 2 to the 4th is 16. That's why it's n to the 4th.